Hello, everyone. Welcome to Sleep Space. Tonight, we will talk about what they didn't teach you about Neptune, the most distant planet in our solar system and one of its most mysterious. So get comfortable, let your thoughts drift, and let's begin our journey into the deep blue unknown. Neptune is often overlooked in favor of its flashier planetary siblings. Mars gets all the attention for its potential to host life, Jupiter for its massive storms and countless moons, and Saturn for its iconic rings. But Neptune quietly orbits at the very edge of our planetary family, cloaked in a rich sapphire hue, hiding secrets that many never learn. You may have been taught that Neptune is just a cold gas giant, far away, mostly made of hydrogen and helium, like Jupiter and Saturn. But that simple version leaves out so much. Neptune isn't just cold, it's active. It's not just far, it's dynamic and powerful. Its winds are the fastest in the solar system, its storms are enormous, and its interior might even contain oceans of liquid diamonds. It is not a frozen, silent world. It is wild, turbulent, and still largely unknown. Let's start with its discovery, because Neptune wasn't found by accident, and that alone sets it apart from every other planet. Unlike all the others visible with the naked eye, Neptune was discovered through mathematics. In the early 1800s, astronomers noticed something strange about Uranus, the seventh planet. It wasn't following its expected path. It wobbled, it strayed from its predicted orbit. At first, people thought maybe the data was wrong, but it kept happening. Two astronomers, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that the odd movement of Uranus could be caused by the gravity of another, unseen planet. Using only mathematics and Newtonian physics, Le Verrier sent his predictions to Johann Galle at the Berlin Observatory. On the night of September 23rd, 1846, Galle pointed his telescope where Leverrier had suggested and found Neptune within 1 degree of where it had been predicted. It was the first planet discovered by math before it was seen by human eyes. But Neptune is not just a mathematical curiosity, it is a world of strange extremes. For one, it's not technically a gas giant like Jupiter and Saturn. It belongs to a class called ice giants. While gas giants are mostly hydrogen and helium, ice giants have more of the heavier elements like water, ammonia, and methane, though they aren't exactly frozen. These ices are more like supercritical fluids, dense and slushy under immense pressure and heat, moving and swirling deep beneath the cloud tops. Neptune's atmosphere is mostly hydrogen and helium, but it also contains methane, and it's that methane that gives Neptune its brilliant blue colour. Methane absorbs red light and reflects blue, creating that distinctive hue. Interestingly, Uranus also has methane, but Neptune appears more vividly blue, possibly due to other, still unidentified atmospheric elements that influence light absorption and reflection. But colour is just the beginning of Neptune's secrets. One of the most astonishing facts about Neptune is its weather. Despite being the eighth planet from the Sun and receiving only about 1/900th the sunlight Earth does, Neptune has the fastest winds in the solar system. These winds can reach speeds of 1,200 miles per hour, faster than the speed of sound on Earth. And that raises a major mystery. Where does Neptune get the energy for such ferocious winds? Unlike Earth, Neptune doesn't have a warm sun heating its atmosphere, yet it has enormous storms, including ones the size of Earth itself. The most famous of these was the Great Dark Spot, first seen by Voyager 2 in 1989. Like Jupiter's Great Red Spot, Neptune's great dark spot was a massive anticyclonic storm, meaning a high-pressure system spinning opposite to Earth's hurricanes. But unlike Jupiter's centuries-old storm, Neptune's vanished within a few years. Then new ones appeared. The planet's storms seem to be born, die, and shift quickly, a sign of a restless and dynamic atmosphere. Voyager 2 remains the only spacecraft to ever visit Neptune. In 1989, it flew just 3,000 miles above the cloud tops, capturing images and data that still form the core of what we know about the planet today. Voyager revealed Neptune's atmosphere in detail, its bands, its storms, its thin rings, and its magnetic field. And Neptune's magnetic field is another strange feature. Like Uranus, its magnetic field is tilted. Not just slightly, but dramatically. It's off-center and tilted by 47 degrees relative to its rotation axis. This suggests that the magnetic field isn't generated deep in a metallic core like Earth's, but rather in a shell of electrically conductive fluid, possibly an ionic ocean of ammonia and water. And because it's so misaligned, the magnetic field wobbles wildly as the planet rotates, making Neptune a complex and chaotic electromagnetic environment. Then there's Neptune's internal heat. Although it receives so little sunlight, Neptune emits more than twice as much energy as it receives. This internal heat source, still not fully understood, powers its storms and atmospheric activity. Some scientists suspect the planet's formation left behind residual heat. Others think radioactive decay or gravitational compression might play a role. But it remains a mystery. Another fascinating theory is that Neptune's interior might have conditions that could create diamond rain. Deep beneath the surface, intense pressure could break down methane molecules, squeezing the carbon into diamond structures that fall like hail through the atmosphere. These diamonds might accumulate in a layer or even form oceans of liquid carbon. It's a concept that pushes the boundaries of what we imagine when we think of planetary geology. Now let's talk about Triton, Neptune's largest moon and one of the strangest in the solar system. Triton is unique. It orbits Neptune in the opposite direction of the planet's rotation, a retrograde orbit, which suggests it wasn't born alongside Neptune, but was captured by it. That capture may have disrupted Neptune's original moon system, causing chaos and collisions. Triton is also geologically active, with cryovolcanoes that erupt not lava, but liquid nitrogen. Its surface is a frozen crust, etched with strange patterns and textures unlike any other moon we've seen. What's more, Triton has an extremely thin atmosphere, made mostly of nitrogen, and it shares a curious resemblance to Pluto in terms of size and composition. In fact, many scientists believe that Triton and Pluto may have had similar origins in the Kuiper Belt, and that studying Triton could give us insight into the distant world of Pluto and other icy bodies beyond. Yet despite all of this, Neptune remains deeply underexplored. No missions are currently headed there, no probes orbit it. We know more about Jupiter's moons than Neptune's entire system. And that silence, that distant darkness, only adds to the mystery. Neptune orbits the Sun once every 165 Earth years. Since its discovery in 1846, it completed its first full orbit in 2011, meaning that in our recorded history, we've only observed Neptune complete 1 year. Its seasons last more than 40 years each. What we see now is just one chapter in a slow planetary story that unfolds across centuries. Even its rings, yes, Neptune has rings, remain largely unknown. Voyager saw faint, dusty rings, possibly unstable, possibly transient. These rings are not the bright, icy ones of Saturn, but dark, thin bands of microscopic material. Some scientists believe they are constantly replenished by tiny moons, while others suggest they may disappear entirely over time. All of these mysteries make Neptune more than just the faraway blue planet. It's a world of extremes, of surprises, of secrets yet to be revealed. What they didn't teach you about Neptune is that it challenges everything we assume about the outer solar system. It forces us to confront our gaps in knowledge and to appreciate that even in our cosmic backyard, much remains undiscovered. So as we drift deeper into Neptune's story, let your mind expand with the vastness of its unknowns. This is a place where physics behaves strangely, where methane becomes ice and carbon becomes diamonds, where storms rage in silence across a frozen sky, and where moons whisper the tales of cosmic collisions from billions of years ago. To understand what makes Neptune so extraordinary, we have to zoom out beyond just facts and figures. Neptune is more than its distance from the Sun, more than its size or temperature. It's a dynamic player in the solar system's history, one whose story is tightly intertwined with the birth and evolution of everything around it. Let's begin with the early solar system, a chaotic, swirling disk of gas and dust. During its formation over 4.5 billion years ago, the planets didn't just emerge quietly and take their places like neatly assigned seats. Instead, they shifted, interacted, and sometimes even swapped positions. Neptune's past may be far more dramatic than you were ever taught. According to the widely accepted NICE model of planetary migration, Neptune may not have always been in the 8th position. In fact, it likely formed closer to the Sun and then migrated outward. The early solar system was crowded with planetesimals, the building blocks of planets. And as Neptune moved through them, its gravity scattered them in every direction. This not only helped clear its path, but also reshaped the orbits of many smaller bodies in the Kuiper Belt. This belt, a vast ring of icy debris beyond Neptune, is like a fossil record of the solar system's ancient architecture. Objects like Pluto, Haumea, and Makemake live there, and Neptune's gravity continues to influence them to this day. In fact, many Kuiper Belt objects, KBOs, are locked in orbital resonances with Neptune. For example, Pluto orbits the Sun twice, for every 3 Neptune orbits. This dynamic relationship keeps Pluto from ever colliding with Neptune despite their overlapping orbital paths. These gravitational dances are not just mathematical curiosities. They're remnants of a time when Neptune, still growing, was shaping the very structure of our planetary neighborhood. When you look at the outer solar system today, you're seeing Neptune's fingerprints everywhere. But there's another piece of the story that's rarely discussed: Neptune's influence on Earth. It might seem absurd to think that a planet nearly 3 billion miles away could have anything to do with us. But Neptune's migration likely disrupted the orbits of countless comets and icy bodies in the early solar system. Some of those objects were flung into the inner solar system and may have played a key role in delivering water and organic molecules to Earth. That means Neptune may have helped seed the very conditions that made life on our planet possible. Without Neptune stirring the pot in the distant solar system, Earth's surface might have remained dry and barren. We owe more to Neptune than you were ever taught in school. Let's now return to the planet itself, and one of its most captivating and least understood features: its energy. Unlike Uranus, which emits roughly the same amount of energy it receives from the Sun, Neptune emits 2.6 times more. This suggests a strong internal heat source, but the mechanism remains mysterious. Some theories suggest that frictional heating in the interior could be caused by the planet's layered structure, where different materials slide against one another under high pressure. Others propose that helium rain or radioactive decay could be providing that extra energy. But why is Uranus so different? The two planets are similar in size, mass, and composition, yet Neptune is active and stormy, while Uranus is relatively calm. This is one of the enduring puzzles in planetary science. It's possible that a massive collision early in Uranus's history knocked it on its side and disrupted its internal structure, leaving it less able to generate heat. Neptune may have avoided such a collision, preserving its energetic core. This brings us to another key element that textbooks rarely explore: Neptune's seasons. Because of its axial tilt, about 28.3 degrees, Neptune experiences seasons much like Earth does. But since it takes 165 Earth years to orbit the Sun, each Neptunian season lasts over 40 Earth years. Summer and winter are slow, drawn-out affairs. As of now, Neptune is moving through its southern summer, which began in the late 20th century. Interestingly, even in summer, Neptune's temperatures remain brutally cold. The upper atmosphere averages around 373 degrees, just 38 degrees Fahrenheit above absolute zero. Yet below that frigid exterior lies a turbulent atmosphere full of activity, storms, and powerful winds. It's a world of contradictions, icy cold on the outside, energetically alive within. And speaking of the atmosphere, Neptune's wind speeds remain one of the most confounding aspects of the planet. These winds, which can reach 1,200 miles per hour, are faster than any recorded on any other planet. They're faster than sound. They're faster than a jet aircraft. These winds aren't just fast, they're surreal. They sweep across the planet's bands, shaping clouds into delicate arcs and stripes. Some clouds appear to be made of frozen methane crystals, forming wispy cirrus-like patterns in the upper atmosphere. But what drives such extreme wind? It's still a mystery. One theory is that Neptune's internal heat rises through the layers and accelerates wind systems in ways we don't yet fully understand. Another possibility is that the planet's relatively low friction, due to its gaseous nature, allows wind speeds to build up over time without being slowed down. What's even more remarkable is that Neptune's storms appear and disappear rapidly. When Voyager 2 flew by Neptune, it observed the Great Dark Spot, a storm the size of Earth. But when the Hubble Space Telescope looked again just 5 years later, it was gone. Later, a new storm formed in the Northern Hemisphere, then another. These storms behave unpredictably, and unlike Jupiter's long-lived storms, Neptune seemed to come and go. Perhaps because of the planet's thin atmosphere or shifting energy patterns beneath the clouds. Let's now go deeper, literally. Beneath Neptune's visible atmosphere lies a complex interior made up of layers we still can't fully probe. The outer envelope is composed of hydrogen, helium, and methane gas. As you go deeper, that gas compresses into a slushy, high-pressure fluid made mostly of water, ammonia, and methane, the so-called ice layer of the ice giant. Further down still, this transitions into a rocky core, perhaps larger than Earth, surrounded by the high-pressure, high-temperature mantles that define Neptune's deep interior. In these extreme environments, molecules behave in ways unfamiliar to us. Methane, under enough pressure, may break apart and reform into carbon structures. That's where the idea of diamond rain comes in. Carbon atoms being squeezed into diamonds and falling through the atmosphere like crystalline precipitation. No spacecraft has ever sent back direct data from Neptune's deep interior. All of this is inferred through models, lab simulations, and indirect observations. But each new piece of data we gather, from telescopes, from spacecraft, from advanced simulations, adds more depth to our understanding. And all the while, Neptune remains quiet. It doesn't reveal its secrets easily. Its distance means radio signals take over 4 hours to reach it from Earth. It reflects just a tiny fraction of the sun's light. It's so remote, it's often left out of popular discussions of planetary science. But that remoteness is part of its power. Neptune forces us to be humble. It reminds us that even in our own solar system, we've only scratched the surface. With all our technology, we've sent probes to Mars, to Jupiter, to Saturn. We've landed on asteroids, flown by comets, even touched the sun's corona. But Neptune, we've been there once, for just a few hours, in 1989, and yet, in those brief hours, Voyager 2 showed us an alien world, more vivid, more violent, and more beautiful than we had ever imagined. Neptune isn't just a planet, it's a window into everything we don't yet know. About planetary weather, about chemistry, about how planets form and change, and possibly about conditions that might exist around other stars. The more we learn about Neptune, the better we can understand the thousands of exoplanets we've discovered across the galaxy, many of which are Neptune-sized or Neptune-like. By studying this quiet giant on the edge of our solar system, we gain insight into worlds far beyond. Neptune becomes a Rosetta Stone, helping us decode the language of planetary formation throughout the cosmos. Now that we've explored Neptune's wild weather, mysterious heat, and forgotten role in the formation of the solar system, let's shift our focus to something even more elusive: Neptune's rings and its complex system of moons. These are the features that rarely make it into textbooks, and yet they hold crucial clues to the planet's history, and maybe to the entire architecture of the outer solar system. Yes, Neptune has rings, though most people don't know this. Unlike the bright, reflective rings of Saturn that can be seen with a modest telescope from Earth, Neptune's rings are dark, thin, and ghost-like. They're composed mainly of microscopic dust particles rather than large icy chunks, which makes them hard to detect and study. These rings are thought to be relatively young and possibly unstable. They're faint, irregular, and uneven. Some sections are clumpier than others. Voyager 2 confirmed the existence of 5 main rings: Gallet, Leverrier, Lassell, Arago, and Adams. The Adams ring is perhaps the most famous because of its curious features known as ring arcs, dense clumps of material that defy easy explanation. Here's the puzzle. Normally, in orbital dynamics, ring material should spread out evenly over time due to gravitational interactions, but the arcs in the Adams ring remain confined to specific locations. It's like trying to spread sugar evenly across a table and somehow ending up with 3 perfectly neat piles that stay there indefinitely. Scientists believe that gravitational shepherding by one of Neptune's moons, Galatea, might be responsible for keeping these arcs stable. But the exact mechanism remains uncertain. The possibility that we're seeing a ring system in the middle of either formation or decay makes Neptune even more compelling. It might be that we're catching the planet in a transitional stage where moonlets are being shredded into rings or rings are coalescing into new moons. Either scenario is a rare opportunity in planetary science, a live act in a story we've mostly only read in the past tense. And speaking of moons, Neptune has 14 known ones, each offering its own set of mysteries. Most of them are small, irregularly shaped, and probably captured objects, leftovers from the early solar system or stolen from the Kuiper Belt. But there is one moon that dominates the system, both in size and in intrigue: Triton. Triton is unlike any other large moon in the solar system. First of all, it orbits Neptune in the opposite direction of the planet's rotation, what's called a retrograde orbit. This alone tells us something strange happened. Triton didn't form with Neptune, it was captured, and that event would have caused tremendous upheaval. When Neptune's gravity pulled Triton into orbit, the capture likely destabilized any original moons Neptune may have had. They may have been flung out of the system entirely, or pulled into Triton's path and destroyed. This capture may also be responsible for the creation of Neptune's rings, debris from shattered moons coalescing into a faint, dusty halo around the planet. Triton itself is geologically active, a shocking fact for a world so cold. Its surface is covered in nitrogen ice, but Voyager 2 observed plumes erupting from the surface, geysers of nitrogen gas shooting 5 miles into space. These cryovolcanoes suggest internal heat, perhaps driven by radioactive decay or tidal forces, even though Triton's orbit is slowly spiraling inward. In the very distant future, billions of years from now, Triton may get so close to Neptune that it will either break apart, forming a spectacular new ring system, or crash into the planet entirely. But what makes Triton even more remarkable is its eerie similarity to Pluto. Both have similar sizes, densities, and surface compositions. They both have nitrogen and methane ice. They both likely originated in the Kuiper Belt, that mysterious region beyond Neptune filled with icy bodies and dwarf planets. Studying Triton is like holding a captured Kuiper Belt object in our gravitational hands. It's a piece of the outer solar system, relocated, repurposed, and still evolving. In many ways, Triton gives us a preview of what missions to Pluto and beyond can reveal. But we haven't visited Triton since Voyager 2 passed by in 1909. Since then, we've sent probes to comets, landed rovers on Mars, and flown helicopters on another planet. Yet Triton, one of the most promising candidates for subsurface oceans and possibly even microbial life, waits in silence, its secret still locked beneath frozen nitrogen plains. Neptune's other moons, though smaller and less studied, still offer surprises. For example, Naiad and Thalassa are tiny, irregularly shaped moons that orbit close to the planet in odd, oscillating paths that avoid collision by engaging in a kind of orbital ballet. Scientists call this a resonance, and it's a phenomenon where gravitational interactions keep two objects from ever getting too close. Then there's Hippocamp, discovered in 2013 using the Hubble Space Telescope. It's just 21 miles across and orbits dangerously close to the larger moon Proteus. Some researchers believe Hippocamp may have formed from debris ejected when something slammed into Proteus long ago. If true, Hippocamp is a newborn in planetary terms, a child of cosmic violence, orbiting its massive parent like a ghost of the past. What's amazing is that Neptune's moon system, though smaller than Jupiter's or Saturn's, may be more dynamic in many ways. It offers us glimpses of captured worlds, collision aftermaths, and moons engaged in gravitational acrobatics. It's a frozen dance of ice and rock in the outer darkness. Despite this, Neptune is criminally underexplored. Since Voyager 2, we've had no dedicated mission to Neptune. NASA and the planetary science community have proposed missions like Trident, a flyby that would explore Triton and Neptune, but they haven't been selected. The costs are high, the distance is daunting, and the time frame's long. A mission launched today wouldn't arrive until the late 2030s or early 2040s. And so Neptune waits, spinning, storming, radiating energy at the edge of our curiosity. In the meantime, scientists use Earth-based observatories, space telescopes, and simulations to continue learning what they can. Every new image from Hubble or the James Webb Space Telescope adds a small piece to the puzzle. But there's no substitute for getting up close. A Neptune orbiter would revolutionize our understanding of the outer solar system. It could map Neptune's magnetic field in detail, analyze its rings, and peer deep into its storms. It could perform dozens of close flybys of its moons, including Triton, to search for signs of geology, chemistry, or even life beneath its icy shell. It could teach us how ice giants form and evolve, something that becomes increasingly important as we find Neptune-sized exoplanets scattered throughout the galaxy. Because here's the thing, in exoplanet surveys, the most common type of planet found is not an Earth twin, it's not a super Jupiter, it's something roughly the size and mass of Neptune. That makes Neptune, in a way, the most typical kind of planet in our galaxy. And yet we know the least about it. We've spent so much time looking inward, toward Earth, Mars, Venus, the Moon, that we've neglected the vast outer reaches. But Neptune is not just a leftover, it is a key to understanding planetary systems as a whole. And there's a strange beauty in the fact that the most average planet type in the universe, the ice giant, is also the most enigmatic in our own solar system. Neptune remains at the edge of visibility, of knowledge, of exploration, but its gravity still reaches across the solar system, influencing distant icy objects, guiding comets, and shaping the architecture of everything that lies beyond it. It is not silent, it is not still. It is a place of storms, heat, and ancient mystery. We've already explored Neptune's winds, storms, moons, and mysterious rings, but now it's time to dive even deeper into the layers of its interior, the unseen forces that generate its intense magnetic field, and the bizarre physics that define what lies beneath those icy blue clouds. What we know, and more importantly, what we suspect about the inner life of Neptune might surprise you more than any textbook ever hinted at. Let's start from the outside and work our way inward. The uppermost layer of Neptune is its atmosphere, made primarily of hydrogen and helium, with a notable percentage of methane. This atmosphere stretches tens of thousands of miles deep and is divided into bands not unlike Jupiter or Saturn. But these bands are subtler. They blend into one another like layered clouds of coloured glass, elegant, almost ethereal, and often invisible in standard optical images. Infrared and ultraviolet observations, however, reveal intense activity in these bands. Jet streams, eddies, and giant storms live within them, driven by mechanisms still not fully understood. As we move below the atmosphere, we enter the mantle of Neptune, a region vastly different from anything we experience on Earth. It's a superheated, high-pressure soup of water, ammonia, and methane, compressed into a state known as a supercritical fluid. This isn't a solid, liquid, or gas. It's something in between, an exotic phase of matter where boundaries between states blur. Molecules move freely like a gas, but remain densely packed like a liquid. Imagine water so pressurized and hot that it behaves more like molten plastic than any ordinary fluid. This is Neptune's true bulk, an enormous layer hundreds of times the mass of Earth, opaque, dark, and electrically conductive. It's in this vast, swirling ocean that Neptune's magnetic field is born. And Neptune's magnetic field is truly one of the strangest in the solar system. Unlike Earth's, which is aligned fairly closely to our planet's rotation axis and generated deep in a metallic outer core, Neptune's magnetic field is wildly tilted, about 47 degrees off axis, and doesn't even pass through the planet's center. Instead, it appears to be generated in a shell surrounding the core, possibly within that ionic, slushy mantle of water and ammonia. The result is a magnetic field that's highly asymmetrical and chaotic. It changes as the planet rotates. It wobbles. It twists and shifts in a way that suggests a magnetic engine located in an unstable region. This behavior hints at a dynamo process very different from the one we experience on Earth, and it may tell us that other planets, particularly ice giants, follow rules of magnetic field generation we haven't yet fully grasped. What's more, the magnetic field traps charged particles in radiation belts. Voyager 2 detected these belts during its brief flyby, noting they were more intense than those around Uranus and almost as powerful as Jupiter's. This was unexpected given Neptune's size and distance from the Sun, but it fits with a broader picture. Neptune, despite being cold, is energetic. It holds power deep inside that expresses itself in ways that defy first impressions. And that brings us even closer to the core. While we've never directly observed Neptune's core, and likely won't for decades, models suggest it's composed of silicates, metals, and perhaps carbon. The pressure at the center is incomprehensibly high, millions of times greater than the atmospheric pressure on Earth. Temperatures soar to thousands of degrees Kelvin, enough to alter the behavior of every known material. Here, exotic physics take hold. Carbon, released from methane deep in the mantle, may crystallize into diamonds under such conditions. The hypothesis that diamonds fall through Neptune's interior like hailstones isn't science fiction. It's grounded in experimental lab simulations on Earth. Researchers have recreated Neptune-like pressures and observed diamond formation in carbon-rich materials. If diamond rain really happens on Neptune, those diamonds wouldn't float. They'd fall, pulled by gravity through the icy mantle, potentially forming a vast layer or ocean of shimmering, compressed carbon. Over time, some of these diamonds might sink all the way to the core, becoming part of a layer never seen by human eyes. It's not just a beautiful idea, it has scientific implications. These diamond layers could help explain why Neptune emits so much internal heat. As diamonds sink, they convert gravitational potential energy into thermal energy, warming the surrounding fluid. That heat then rises, feeding storms and wind patterns we observe in the atmosphere. It's a feedback loop, born in pressure, visible in clouds. Now let's take a moment to think about time. Neptune's rotation period is just under 16 hours. Despite being massive, it spins quickly, creating a noticeable equatorial bulge. This rapid rotation helps maintain its weather systems and affects its magnetosphere's shape, causing distortions and warping that ripple through its magnetic environment. These ripples affect everything from atmospheric chemistry to space weather around the planet. Aurorae have been detected near Neptune's poles, not the brilliant curtains of light like Earth's, but subtle, far ultraviolet emissions observed by sensitive instruments. These aurorae tell us about the interactions between solar particles, Neptune's magnetic field, and its upper atmosphere. Even out at the edge of the solar system, where the Sun is just a bright point in the sky, its influence is still felt. That faint solar energy also plays a role in Neptune's cloud formations. Despite the cold, Neptune has a surprisingly dynamic weather cycle. Methane condenses into clouds, forming bright, white patches that race around the planet at incredible speeds. Some clouds are long-lived, others form and dissipate in hours. High-altitude clouds, particularly those composed of methane ice, act like tracers, revealing the winds that drive them. The contrast between Neptune's internal heat and the faint sunlight it receives sets up powerful thermal gradients, meaning huge differences in temperature from one region to another. These gradients drive convection, which in turn creates storms and jet streams. But Neptune's storms don't just resemble hurricanes, they also exhibit complex vertical structure. The tops of the clouds can spin in one direction, while lower levels move the opposite way. It's a multi-layered dance of gases, pressured by forces we're only beginning to understand. And yet, for all its violence and volatility, Neptune is also quiet in its own way. It makes no sound, it has no solid surface, it exists in stillness and pressure, its blue hues masking the chaos beneath. It doesn't shine with its own light, and it doesn't scream for attention like Saturn with its rings or Jupiter with its great red spot. It waits, cold, fast, luminous only in reflected light. A mysterious engine churning at the edge of everything we know. It's easy to overlook a planet like Neptune. You have to want to understand it. You have to dig. But the deeper you go, the more strange and wondrous the picture becomes. What they didn't teach you about Neptune is that it breaks rules. It rewrites expectations. It behaves unlike any other planet. And yet, it may be the blueprint for worlds throughout the cosmos. Billions of exoplanets have been found. Many are Neptune-like, ice giants with atmospheres rich in hydrogen and helium, orbiting other stars, some close, some far, some scorched, some frozen. And all of them are mysteries, distant blue question marks. By studying Neptune, we create a bridge between what we can observe here and what we guess about over there. The physics of Neptune help us model distant atmospheres. The chemistry of its interior helps us predict what might lie inside other planets. And the behavior of its magnetic field helps us understand how dynamos can evolve in strange and shifting environments. In this way, Neptune isn't just a planet, it's a proxy. A puzzle piece that connects Earth to alien worlds. A testing ground for ideas, theories, and models that might one day apply to planets orbiting distant suns. And that, perhaps, is the most astonishing thing they didn't teach you about Neptune. It may be far away, it may be quiet, but it may also be the most important planet in the solar system for understanding the universe beyond. Now that we've gone deep into Neptune's interior, it's time to zoom out again, not to the surface, but beyond. Because one of the most fascinating things about Neptune isn't Neptune itself, it's what surrounds it. Tonight, we're going to talk about Neptune's place in the solar system, its history, its migration, its gravitational influence, and the incredible story of how it might have shaped or reshaped the architecture of everything we know about our cosmic neighborhood. Let's begin in the early solar system. Over 4.5 billion years ago, the Sun was surrounded by a massive disk of dust and gas, the solar nebula. Within this spinning cloud, particles clumped together into planetesimals. Some of these collided and merged, forming rocky worlds near the Sun, while others, farther out, accumulated gas and ice to become the giant planets. At some point in this process, Neptune formed. But here's the twist. Neptune didn't form where it is now. According to the Nice model, a widely supported theory named after the city in France where it was developed, the giant planets didn't start in their current orbits. Instead, they began much closer together and over time migrated outward. Neptune, in particular, may have formed closer to Saturn and Uranus and slowly moved to its current position, a staggering 4.5 billion kilometers from the Sun. This migration wasn't smooth, it was chaotic, it was violent, and it changed everything. As Neptune moved outward, its gravity ploughed through the outer solar system like a cosmic snowplow. It scattered countless icy objects, disrupted forming bodies, and restructured entire regions of space. One of the most profound results of this gravitational movement was the shaping of the Kuiper Belt. The Kuiper Belt is a region of frozen bodies beyond Neptune, stretching from about 30 to 55 astronomical units from the Sun. It's home to dwarf planets like Pluto, Haumea, and Makemake, and to countless other icy rocks, comets, and proto-worlds. But many of these objects have orbits that seem organized. They're clustered, resonant, locked in gravitational patterns that only make sense if Neptune moved. Some Kuiper Belt objects, like Pluto, are in what's called a 2-3 resonance with Neptune. That means for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This orbital dance ensures that they never collide, even though their paths cross. It's a kind of gravitational choreography, written billions of years ago. What they didn't teach you about Neptune is that it's a sculptor, an architect. It helped carve the edges of the solar system. Its movement created gaps, rings, and reservoirs of frozen matter that still orbit out there in silence. Some of those scattered objects became long-period comets. Others may have been ejected into interstellar space. And that's just the beginning. There's evidence that Neptune's migration triggered a late heavy bombardment, a period, roughly 4 billion years ago, when the inner solar system was pelted with asteroids and comets. Craters on the Moon, Mars, and Mercury point to this violent chapter, and it might never have happened if Neptune had stayed where it was. So in a very real way, the conditions that made Earth what it is, including its oceans, its climate, and maybe even the arrival of water-rich comets, may have been influenced by Neptune's ancient journey. Let's talk about Neptune's gravity a little more. This planet may seem far away and isolated, but its gravitational field still reaches out, pulling on comets, nudging other planets, and shaping the orbits of distant objects in ways we're still discovering. Some of the most interesting discoveries in recent decades involve so-called detached objects, distant icy bodies like Sedna and 2012 VP-113. These strange, elongated orbits take them far beyond the Kuiper Belt. They don't interact with Neptune directly, but they're too close to be unaffected by its gravity. Some scientists suspect that Neptune, during its outward migration, tossed these objects into eccentric orbits. Others suggest something more, that Neptune might have hinted at the existence of something even bigger. And that brings us to one of the biggest mysteries in astronomy today, Planet 9. For years, researchers have noticed that certain distant objects, far beyond Neptune, behave oddly. Their orbits are clustered, tilted, not random. Something appears to be shepherding them, something massive, something dark, and something that hasn't yet been seen. This hypothetical world, dubbed Planet 9, would be several times more massive than Earth, located hundreds of astronomical units away. And if it exists, its orbit may have been influenced, or even initiated, by Neptune's gravitational chaos billions of years ago. Think about that. Neptune, a world of ice and clouds, could be the reason we're even searching for another planet right now. Its fingerprints may be all over the solar system's distant frontier. But even without Planet 9, Neptune's gravitational influence continues to astound us. Consider Neptune's interaction with Pluto. While Pluto is famously a dwarf planet, it's also a kind of companion to Neptune. Their orbits are tied together, not in a physical way, but in a gravitational one. Because of their 2-3 resonance, Pluto is always kept at a safe distance from Neptune. It never comes close enough to crash, or even pass nearby. Their timing is perfect, like dancers circling a cosmic stage, each one moving in time with the other. This relationship teaches us something profound. Gravity isn't just about pulling. It's about rhythm, about timing, about balance. Neptune doesn't just tug on Pluto, it guides it, protects it, holds it in a pattern that's lasted for billions of years. And there are other, less visible consequences of Neptune's presence. The shape of the Kuiper Belt, the gaps in asteroid populations, the creation of the scattered disk, a region of icy bodies with chaotic, elongated orbits. Even some of the long-period comets we see diving toward the inner solar system may have been tossed out by Neptune's gravity, only to return millions of years later on their giant elliptical paths. What they didn't teach you about Neptune is how important it is to the solar system's story. It's not just a distant sphere floating in darkness, it's an active participant in the system's evolution, a mover, a shaper, a planet that, despite being remote and quiet, has changed everything. It reminds us that in space, distance doesn't mean irrelevance. And here's one more layer to this puzzle. In recent years, astronomers have discovered thousands of exoplanets, planets orbiting other stars, and a huge number of them are Neptune-like. These are sometimes called mini-Neptunes or sub-Neptunes, planets a few times the size of Earth, with thick atmospheres of hydrogen and helium. Some are hotter than Mercury, others are colder than Pluto, but many appear to be more common than gas giants like Jupiter. In fact, if we look at the galaxy as a whole, Neptune-like planets might be the most common type of planet out there. Think about that. Neptune isn't just a planetary oddity in our system. It might be the archetype of worlds across the cosmos. Studying Neptune means studying the template for countless alien worlds. It's like holding the key to understanding planetary systems everywhere. Its blue glow, its icy mantle, its strange magnetic field, these might be normal traits in the galaxy, not exceptions. So while textbooks may have glossed over Neptune, while diagrams may have shown it as a small dot on the edge of our system, the reality is that Neptune is central to our understanding of how solar systems are born, how they change, and what kinds of worlds might be out there waiting to be discovered. Why do we know so little about Neptune? Why, in a world where we've landed rovers on Mars and flown helicopters on Triton, is Neptune still such a distant enigma? To understand this, we need to talk about exploration, about technology, and about the future of our journey toward the outermost planets. Let's begin with a single name: Voyager 2. In 1989, NASA's Voyager 2 spacecraft became the first and only spacecraft to visit Neptune. After launching in 1977, it traveled more than 4 billion kilometers over the course of 12 years to perform a brief flyby, a high-speed glance that lasted just a few hours. But those few hours changed everything. Voyager 2 sent back the first close-up images of Neptune, revealing a surprisingly active world. It captured the Great Dark Spot, a massive storm system. It measured Neptune's magnetic field. It discovered 6 new moons and several faint rings. It confirmed the presence of fast-moving winds and icy clouds of methane. But as incredible as that encounter was, it was just that. a moment. Voyager didn't orbit, it didn't land. It simply passed by, sending back snapshots from millions of kilometers away. And then it continued outward into interstellar space. Since that day in 1989, no other spacecraft has visited Neptune. That's right. In over 35 years, we haven't sent a single dedicated mission to this vast, mysterious world. Not a probe, not an orbiter, nothing. So much of what we know about Neptune is actually built on inference, educated guesses based on distant observations, theoretical models, and brief glimpses. Why? The answer is simple and complicated at the same time. Distance. Neptune is incredibly far. Over 30 astronomical units from the Sun. That's more than 30 times the Earth-Sun distance. It takes light from the Sun over 4 hours to reach Neptune. By comparison, it takes light just 8 minutes to reach Earth. Sending a spacecraft that far isn't just hard, it's expensive, slow, and logistically complex. Even with modern propulsion, it would take 10 to 15 years for a mission to reach Neptune, depending on gravity assists and the launch window. And once it arrives, you're dealing with extremely weak sunlight, intense radiation from charged particles, and vast communication delays. A round-trip signal between Earth and Neptune takes nearly 9 hours. On top of that, planetary science budgets are limited, and for decades, Mars has taken the spotlight. It's closer, more Earth-like, and easier to study in detail. Jupiter and Saturn, too, have received much more attention. Missions like Juno and Cassini spent years orbiting those giants. Neptune, meanwhile, has waited, but that may be changing. Right now, several mission concepts are being proposed to explore Neptune more deeply than ever before. Some are still on paper, others are in early design stages. All are incredibly ambitious. Let's look at a few of them. One of the most promising ideas is a mission called Neptune Odyssey. Proposed by NASA scientists, this would be a flagship-class orbiter, similar in scale to Cassini, designed to orbit Neptune for many years. It would study the planet's atmosphere, rings, magnetic field, and moons in detail. It could deploy an atmospheric probe to descend into Neptune's clouds, transmitting data as it falls. Imagine that for a moment, a robotic eye falling through Neptune's atmosphere, measuring temperature, pressure, composition, watching the clouds rush by as it dives into a storm system, sending back real-time data from a place no one has ever touched. Then there's Triton, a proposed flyby mission to Neptune's moon Triton. Triton is especially fascinating. It's one of the only large moons in the solar system that orbits backward, suggesting it was captured from elsewhere. It's also geologically active, possibly harboring a subsurface ocean. Triton would make a close pass by Triton, mapping its surface, measuring its magnetic field, and looking for plumes or other signs of cryovolcanism, the icy equivalent of lava. Other mission concepts include solar sail probes, nuclear-powered orbiters, and even multi-world missions that would visit both Uranus and Neptune over a longer timeline. But here's the challenge. These missions take decades. From planning to launch to arrival, exploring Neptune is a generational effort. If we launch a Neptune orbiter in the early 2030s, the best possible window, it might not arrive until the late 2040s or early 2050s, which means that many of the scientists and engineers working on these missions today may be retired by the time the data starts coming back. Some may not even live to see the results. This is one of the things they didn't teach you about Neptune. Exploring it isn't just an act of science, it's an act of faith, a commitment to discovery that spans lifetimes. a belief that the pursuit of knowledge is worth the wait. Still, the payoff would be enormous. A Neptune orbiter could answer so many lingering questions. What drives its supersonic winds? What's really inside that icy, metallic core? How do its rings evolve over time? Are its magnetic anomalies unique or common among other ice giants? Does Triton really have a subsurface ocean, and could it harbour life? Triton, by the way, might be the most overlooked candidate for extraterrestrial life in the entire solar system. Captured from the Kuiper Belt, it's likely a world similar to Pluto, but bigger and geologically active. If it has liquid water beneath its crust, heated by tidal forces from Neptune's gravity, it could potentially host microbial ecosystems in dark, salty oceans. Just like Europa or Enceladus, moons already famous for their life-harboring potential, Triton could be hiding life. And yet it receives a fraction of the attention. But not forever. With every passing year, the push to send a mission grows stronger. Public interest is rising, scientists are organizing, space agencies are listening. One day, maybe in your lifetime, we'll have a spacecraft orbiting Neptune, diving into its storms, mapping its moons, and sending back high-resolution images of a world we've only glimpsed once. Until then, we rely on telescopes. The Hubble Space Telescope has offered occasional views of Neptune, capturing new storm systems and monitoring atmospheric changes. The James Webb Space Telescope, with its infrared capabilities, has already started to reveal new details, including temperature patterns and cloud structures. But even JWST, as powerful as it is, can't replace a close-up mission. Telescopes see the light. Spacecraft feel the environment. They measure particles, sniff atmospheres, dive through radiation belts, and fly just kilometers from moons. Neptune deserves that kind of attention, because what they didn't teach you is that Neptune may be holding secrets we can't even imagine, about planets, about atmospheres, about the very structure of solar systems. It may be the template for alien worlds across the galaxy. And yet it remains, for now, mostly unseen. As we close out this section, think about this. In the dark silence beyond Neptune lies a boundary, the edge of the solar system. Beyond it are the scattered icy bodies of the Kuiper Belt, and eventually the vast nothing of interstellar space. Neptune is our last great century, the final major planet before the cosmic ocean begins. One of the most intriguing features of Neptune is its system of moons. While Neptune is not the planet with the most moons in the solar system, the ones it does have are some of the most mysterious. It has 14 known moons, and among them, Triton stands out as one of the most extraordinary. Triton is not just Neptune's largest moon, it's one of the most fascinating objects in the entire solar system. Triton orbits Neptune in a retrograde motion. That means it moves in the opposite direction of Neptune's rotation, a behavior that's incredibly rare among large moons. This strange orbit is a powerful clue that Triton didn't form alongside Neptune. Instead, it was likely a captured object, possibly a dwarf planet from the Kuiper Belt that Neptune pulled into its gravitational influence billions of years ago. This capture scenario wasn't a gentle process. In fact, when Triton was caught by Neptune's gravity, it probably caused chaos in Neptune's original moon system. Many of those moons may have been ejected, destroyed, or collided with each other. Triton, being massive and newly introduced, would have destabilized any smaller natural satellites that had formed with Neptune. The few moons that remain today, such as Nereid and Proteus, likely survived because of either lucky positioning or later formation. Triton's surface is covered in a layer of frozen nitrogen, and beneath it lies a crust of water ice. This surface reflects a large portion of sunlight, giving Triton a very bright appearance. But what lies underneath may be even more fascinating. There's evidence to suggest Triton could have a subsurface ocean, similar to moons like Europa and Enceladus. If that's the case, then Triton may be yet another potential home for microbial extraterrestrial life. What makes Triton even more surprising is its geological activity. Despite being so far from the Sun, it is one of the few moons in the solar system known to be geologically active. Voyager 2, the only spacecraft to have visited Neptune and Triton, captured images of active geysers erupting from the surface. These geysers appear to spew out nitrogen gas and dark dust particles up to 8 kilometers into the sky, a behavior that seems almost impossible for a frozen world that far out. This kind of activity suggests that Triton is not a dead world. There are internal forces at work, likely from tidal heating caused by its interaction with Neptune's gravity. Although its retrograde orbit is slowly spiraling Triton inward toward Neptune, creating friction and heat, it also means that one day, far in the future, Triton will likely be torn apart and could form a ring system around Neptune. This possibility reminds us of how dynamic and ever-changing even the outermost regions of our solar system can be. Beyond Triton, Neptune's smaller moons hold their own mysteries. Nereid, for instance, has one of the most eccentric orbits of any moon, swinging dramatically closer and farther from Neptune during its orbit. This unusual path is another clue to the violent gravitational reshuffling that took place after Triton's capture. Then there's Proteus, a moon so large and close to Neptune that it should have been torn apart by tidal forces. But Proteus appears stable, at least for now. Its irregular, non-spherical shape and battered surface tell the story of a body that has taken a lot of cosmic punishment. It likely formed from debris left over after the system settled following Triton's arrival. Another curiosity is Neptune's moon Naiad, which has a particularly bizarre orbital resonance with its neighbouring moon, Thalassa. These two moons essentially dance around each other in a pattern that prevents collisions. Naiad zips around Neptune every 7 hours, while Thalassa takes about 7.5. Their orbital paths are inclined and offset in such a way that Naiad passes above and below Thalassa in a cosmic ballet that astronomers call an orbital resonance. This kind of resonance requires incredible precision. Over millions of years, gravitational nudges have refined their orbits into a stable configuration. It's a stunning example of the natural choreography that happens when gravity and time work together over astronomical scales. These interactions between Neptune's moons give us insight into the system's history. They tell us about the migration of Triton, the loss of earlier moons, and the dynamic balancing act that shaped what we see today. Each moon is a window into a past that was violent, chaotic, and surprisingly creative. We often think of the outer solar system as cold and quiet, but Neptune's moons tell a different story. There's activity, motion, and even heat, signs that these distant objects are more than just frozen relics. They are places of energy, potential, and ongoing transformation. These discoveries are a reminder of how much we still don't know. Voyager 2's 1989 flyby gave us a tantalizing glimpse, but since then, we've never returned. No other mission has visited Neptune, and that leaves Triton and its siblings largely unexplored. What geysers still erupt unseen? What oceans still slosh beneath ice? What secrets remain locked in their cores? The potential for future missions to explore Triton is high on the wish list for planetary scientists. With the right instruments, WITSAR could study its geysers up close, map its surface in detail, and probe beneath the ice for liquid water. The chance to explore a moon with a possible subsurface ocean, and one that was likely born far from Neptune, is a scientific opportunity too important to ignore. In many ways, Triton could be a time capsule from the early solar system. If it was indeed captured from the Kuiper Belt, then studying it could teach us not just about Neptune, but about the formation and migration of planets and icy bodies throughout our entire solar system. It's like a lost sibling of Pluto, drawn in by Neptune's pull and forever changed by that fateful encounter. Neptune's moons reveal that even in the dark outskirts of the solar system, complexity and wonder thrive. They show us that planets and their companions are not static, but part of a larger, dynamic, evolving dance, one that continues to unfold even now, far beyond the reach of ordinary light. By now, we've journeyed through the basic features of Neptune, its strange magnetic field, its gravitational dance with moons, its long-distance influence across the solar system. But there's still a part of Neptune that's as elusive as it is fascinating. The deep forces and mechanisms shaping its atmosphere. We've seen the surface storms, the great dark spot, and the raging winds. But to understand what's really going on, we need to dig deeper, past the clouds, past the dark spots, to the forces that drive the whole system.
Neptune's atmosphere is not only complex, it's one of the most extreme environments we know in our solar system. Even though Neptune is far from the Sun and only receives a fraction of the sunlight Earth does, it has an incredibly energetic atmosphere. In fact, it's one of the most energetic atmospheres of any planet.
While the Sun provides some heat, it's not enough to explain the incredible storms and super-fast winds we observe. In fact, Neptune emits more heat than it receives from the Sun. This mysterious excess heat has puzzled scientists for decades. After all, you would expect a planet so far from the Sun, with temperatures hovering around 200 degrees Celsius, to be a frozen wasteland. But it's not. Scientists believe the heat is coming from deep within Neptune, likely from its interior, possibly from tidal heating generated by interactions with its moons, particularly Triton. As Triton orbits Neptune in its backward retrograde orbit, its gravitational interactions with the planet create friction within Neptune's mantle, generating heat and driving some of the planet's atmospheric dynamics. This energy, coming from deep inside the planet, helps fuel Neptune's violent storms and winds. These winds can reach speeds of over 2,100 kilometers per hour, 1,300 miles per hour, faster than the speed of sound on Earth. For comparison, the fastest winds on Earth, those in the most intense tornadoes, are just a fraction of that speed. The winds on Neptune aren't just fast, they're powerful. These atmospheric jet streams carve deep into Neptune's atmosphere, creating dark spots that have been observed for years. These spots are essentially giant storm systems, similar to Jupiter's Great Red Spot, though much darker in appearance. They can last for months or even years, shifting across the planet's surface with disturbing ease. The Great Dark Spot, which was first observed by Voyager 2, is one of the most famous features of Neptune's atmosphere. It's essentially a massive storm system, complete with cloud formations, winds, and turbulent conditions. But the Great Dark Spot isn't permanent. After Voyager's encounter, astronomers noticed that it disappeared within just a few years. In 1994, it was replaced by another similar storm, dubbed the Second Dark Spot. This pattern of dark spots appearing, shifting, and disappearing is characteristic of Neptune's dynamic and constantly changing atmosphere. While we don't fully understand the specific atmospheric dynamics, what we do know is that Neptune's storms are incredibly volatile, with complex wind patterns and atmospheric interactions that set it apart from other planets in the solar system. What's particularly intriguing is how Neptune's storms compare to those on Jupiter and Saturn. Jupiter's storms are large and persistent, while Saturn's are more stable and well-structured. Neptune's storms, by contrast, seem to form, evolve, and dissipate with little predictability. This suggests that Neptune's atmosphere is not only more energetic than expected, but also more chaotic in nature. But these violent storms are just one part of the picture. Neptune's atmosphere also features banded cloud structures that we see in both optical and infrared observations. These bands, dark, light, and in between, represent variations in the composition of the atmosphere. The lighter bands are rich in methane ice clouds, while the darker bands are composed of deeper, more turbulent layers of gases. Some scientists believe that the darker clouds represent areas of downward motion, where the planet's atmosphere is sinking into the deeper layers of the atmosphere, possibly bringing up heat from within. Meanwhile, the lighter clouds represent regions where air is rising, releasing methane ice and other compounds into the upper layers of the atmosphere. And here's another mystery. Why is Neptune so blue? Unlike Uranus, which also has a methane-rich atmosphere but appears more greenish, Neptune's atmosphere is a deep, rich blue. This is because methane absorbs red and infrared light from the sun, reflecting only blue wavelengths. The presence of methane in Neptune's upper atmosphere gives the planet its striking colour, but it's still unclear whether there are additional compounds at work in creating such a rich, vibrant blue. And let's not forget the extreme cold that defines Neptune's atmosphere. The average temperature in the upper layers of the atmosphere is around 200 degrees, but because Neptune is constantly being bombarded with energy from within, its cloud tops, the visible part of the atmosphere, are actually much warmer than you might expect for a planet this far from the Sun. In fact, the temperature difference between the upper and lower parts of Neptune's atmosphere is much larger than we see on Earth. This significant temperature gradient helps drive the intense winds and the formation of storm systems. The greater the difference in temperature, the more energetic the system becomes. And Neptune's atmosphere is definitely energetic. What they didn't teach you about Neptune is that its atmosphere is a laboratory for extreme conditions. It is an environment where winds exceed the speed of sound, where storms change rapidly, and where internal heat defies expectations. It's a world that demonstrates the vast complexity of planetary atmospheres and offers insights into how other gas giants and ice giants, like exoplanets, might behave under similar conditions. But even more fascinating is the fact that the deeper we look into Neptune's atmosphere, the more questions emerge. Scientists are still working to figure out how its atmosphere operates, what causes its storms to appear and vanish, and how energy is transferred between the planet's interior and outer layers. The study of Neptune's atmosphere will continue for decades to come. Future missions, whether flybys like Triton or orbital missions like Neptune Odyssey, will help us uncover the mysteries of its dynamic weather systems. These missions may provide insights not only into Neptune itself, but into the processes that govern all planetary atmospheres, from the icy worlds of the outer solar system to the hot, stormy planets orbiting distant stars. Neptune's weather, storms, and atmosphere may be alien in many ways, but they're a reminder of how much we have yet to discover in the solar system. As we continue to study Neptune and the other ice giants, we'll undoubtedly unlock new insights into the nature of our solar system and the countless other solar systems out there teeming with exoplanets. Neptune is not only fascinating because of its storms, moons, and magnetic mysteries, it also has an enigmatic system of rings that adds another layer of intrigue to this distant world. When we think of planetary rings, Saturn's spectacular shimmering bands often come to mind, but Neptune's rings are far less obvious, more subtle, and full of surprises that challenge our understanding of how rings form and behave. Neptune's rings are faint, narrow, and clumpy. Discovered during the 1980s through ground-based observations and confirmed by Voyager 2's flyby in 1989, these rings are not continuous bands like Saturn's. Instead, they are composed of arcs, partial ring segments that are denser and brighter than the surrounding ring material. These arcs are peculiar structures, held together in a delicate balance that scientists are still trying to fully understand. Why does Neptune's ring system consist of arcs instead of full rings? This question puzzled astronomers for years. The leading explanation involves gravitational interactions with Neptune's moons. Small moons orbiting near or within the rings act as shepherds, confining the ring particles and maintaining the arc shapes. These moons' gravitational pulls keep the particles from dispersing evenly around the planet, creating clumps of material in specific regions. One of these moons, Galatea, plays a crucial role. Orbiting just inside Neptune's main ring, Galatea's gravity exerts a strong influence, stabilizing the arcs. Yet this stability is fragile. The arcs are dynamic. Over time, they shift and change shape. In fact, observations show that the arcs slowly drift, evolve, and even vanish and reappear. This suggests that the arcs are not permanent, but temporary features maintained by a complex gravitational dance. Neptune's rings are composed of tiny, dark particles, likely a mix of ice and dust, coated with radiation-processed organics that give them a reddish or greyish hue. Unlike Saturn's bright, icy rings, Neptune's are much darker and more diffuse, making them harder to detect. This dimness is why they remained undiscovered for so long. Voyager 2 provided the first detailed images of Neptune's rings, revealing 5 distinct rings named after astronomers who contributed to Neptune's study: Gale, Leverrier, Lassell, Arago, and Adams. The Adams ring is where the famous arcs reside. Scientists have theorized that Neptune's rings may be relatively young, perhaps only a few 100 million years old. They might have formed from debris generated by collisions between moons or the breakup of small objects that wandered too close to Neptune's gravity. Interestingly, the rings and arcs help us understand broader processes about how planetary ring systems form and evolve. They suggest that rings can be temporary features, influenced by moons and gravitational forces, rather than stable, ancient structures. Beyond the physical composition, Neptune's rings also interact with the planet's magnetosphere and charged particles trapped in its magnetic field. These interactions affect the ring's structure and particle dynamics, causing dust to be removed or redistributed. Charged particles can erode ring particles, gradually changing their size and reflectivity over time. What they didn't teach you about Neptune's rings is that they're more like living structures than static bands. They respond to gravitational nudges, magnetic forces, and collisions, constantly evolving in subtle but significant ways. Beyond rings, Neptune's magnetosphere is another realm of mystery. Neptune's magnetic field, as we discussed before, is unusually tilted and offset from the planet's center, creating a magnetic environment that is chaotic and ever-changing. This complex field traps charged particles, forming radiation belts similar to Earth's Van Allen belts, but more irregular. These trapped particles interact with Neptune's atmosphere and rings, producing faint auroras near the poles. Unlike Earth's bright auroras, Neptune's are subtle ultraviolet glows, detected by telescopes like Hubble. These auroras are caused by charged particles spiraling along magnetic field lines and colliding with atmospheric gases. The magnetosphere's odd shape means that it sometimes allows solar wind particles to penetrate more deeply into the atmosphere than on other planets. This interaction may also influence Neptune's atmospheric chemistry, possibly contributing to the formation of hazes and complex hydrocarbons in the upper atmosphere. Moreover, Neptune's magnetic field's tilt and offset create unique challenges for understanding how dynamos operate in ice giants. Unlike the Earth or Jupiter, where the magnetic field aligns more closely with the rotation axis, Neptune's misaligned field suggests a dynamo operating in a thin shell, perhaps within the conductive layers of its supercritical fluids. Studying this unusual magnetosphere helps scientists understand not only Neptune, but also other ice giants in our galaxy, many of which likely have similarly tilted fields. This knowledge is essential for interpreting signals from exoplanets detected around distant stars. As we consider Neptune's rings, magnetic field, and atmospheric interactions, a picture emerges of a dynamic, interconnected system. Each component, from the tiny ring particles to the giant magnetic bubbles, plays a role in shaping the planet's behavior. And yet, so much remains unknown. Future missions to Neptune could map its rings in unprecedented detail, observe changes in real time, and probe the magnetosphere to understand its complex structure. Such missions might also measure the composition and age of ring particles, unraveling the history encoded in these faint bands. Neptune's rings and magnetosphere remind us that even the faintest features of a planet can reveal profound secrets about its history, its environment, and the forces at work within and around it. Neptune stands as a silent giant at the edge of our solar system, shrouded in mystery and wonder. Over the course of this journey, we've uncovered how much this distant world hides beneath its cold, blue exterior. From its violent storms and supersonic winds to its complex moons, faint rings, and oddly tilted magnetic field. Yet, what they didn't teach you about Neptune is that it is far more than just a planet of ice and gas. It's a keystone to understanding the broader cosmic story. Neptune's story begins in the chaotic early solar system, where it migrated outward, reshaping the orbits of countless icy bodies and influencing the entire structure of our planetary neighborhood. Its gravitational reach extends far beyond its visible form, affecting distant objects in the Kuiper Belt and possibly hinting at worlds yet to be discovered. The icy giant's atmosphere challenges our models with storms faster than sound, unexpected internal heat, and dynamic cloud systems that change faster than we can track. Its magnetic field's wild tilt and offset tell a tale of a planet unlike any other, while its moons, especially Triton, offer clues to planetary capture and the potential for hidden oceans beneath frozen surfaces. Even Neptune's rings, faint and fragmented, are dynamic laboratories of gravity and particle physics, telling stories of formation, destruction, and cosmic balance. And yet, for all we know, Neptune remains one of the least explored planets in our solar system. Voyager 2's brief flyby gave us tantalizing snapshots, but it's only a whisper compared to the vast complexity lying beneath. As we look forward, the future missions proposed to explore Neptune promise to transform our understanding. Whether by orbiting this distant world, sending probes into its atmosphere, or closely studying Triton's potential oceans, humanity's next steps will unlock secrets that have eluded us for decades. But what does all this mean for us here on Earth? Why does Neptune matter beyond being a distant icy dot? For one, Neptune teaches us about the diversity of planetary systems. It's a window into worlds far beyond our own. From the mini-Neptunes orbiting other stars to the processes shaping solar systems across the galaxy. More intimately, Neptune's influence on the early solar system may have had direct consequences for Earth. The late heavy bombardment, possibly triggered by Neptune's migration, delivered water and organic materials that set the stage for life. And perhaps most fittingly for sleep space, Neptune invites us to embrace the vastness of the cosmos with a calm, curious mind, to recognize that even the coldest, most distant worlds are part of the story that connects us all. As you drift towards sleep tonight, think of Neptune, a giant world swirling with storms, dancing moons, and rings of icy dust, quietly shaping the universe, just out of sight but never out of influence.
May its mysteries inspire your dreams and fuel your curiosity until the day we finally unlock all the secrets this distant world holds.
Thank you for joining me on this deep dive into what they didn't teach you about Neptune. Sleep well and keep looking up.